So we're moving next into multi-component flash design. So far we've dealt with flash drums where we've only had two components, usually A and B, and we've been able to use these graphical methods to solve them and so forth. Well, we're going to move beyond that to the case where we have a flash drum, but we have more than two components coming in. We may have up to n components, and the equations become a little more complicated. But it's certainly feasible to solve these type of systems. And so I've shown you here just the flash drum with a flow rate F and the molar concentrations or mole fractions coming in at Zi, again where I can be species 1, 2, 3, etc. all the way up to N. And then we have a flow rate V, flow rate L, and then the mole fractions in the vapor phase and the mole fractions in the gas phase. And this is the type of typical setup we've dealt with before. So a typical problem that we may deal with is shown here, where we're given some information. We're given the total pressure and the temperature of this flash drum. So we're given the temperature and the total pressure. We're given a feed rate coming in, and we're giving the mole fractions of the feed coming in here. And we're asked to find information about the outlets. We want to know the mole fractions of the liquid and vapor of the different components and the flow rates of the vapor and the liquid. And so this is a typical type of problem we'll have. We've dealt with before, but also especially when we're dealing with multi-component flash drums. So let's look at the equations that apply to this type of system. First, let's write out our material balance equations. These are our multiple material balance equations. This is the overall balance, and then we'll have various material balance equations for the different species. So before, we've only dealt with one material balance equation of this type usually because we've only had two species. So remember that the number of species we have, minus 1, will tell us how many independent of these material balance equations we have. But we can write out various material balance equations for the different chemicals coming in and out of our flash drum. Next, we can write out some equilibrium, vapor-liquid equilibrium equations. And that's this equation right here. It just says that the mole fraction in the vapor phase is equal to the K value times the mole fraction in the liquid phase. So we've seen this before, but let's just write it all out. And again, for each different species, we can write out a vapor-liquid equilibrium equation for those particular species. The last set of equations I'm showing you right here, where we have the summation of the mole fractions in the liquid phase or the vapor phase here, they add up to 1. And so these are the set of equations that apply to this multi-component flash drum. And we're going to use these equations to go about solving for a solution to this problem where we're given information about the feed, but we want to find information about the outlet. If I go ahead and take all of these four equations, do some algebraic manipulation, go ahead and solve them for x and y, I can rewrite them and get these two equations here. And if you look in the WANCAT book, you'll see that these equations are listed in there. And these are just the two equations for a multi-component flash drum that tell us what xi is and yi. So we can go ahead and get these various mole fractions of the liquid and vapor. And so these are the two components we're going to worry about, or two equations that we're going to worry about. So again, here's our two equations for xi and yi. Let's look at how we actually use these equations to go about solving for our flash drum. So the problem with the flash drum is we may not necessarily know what V is right here, V's are. And so we have difficulty in actually going about solving for what yi and xi are. So I've just written here two other equations, and these are from previous page also. But the summation of the mole fractions in the vapor equals 1, summation of the mole fractions in the liquids equals 1. If I take these xi's and these yi's, plug them into these equation here, take one, subtract the other, so in this case 1 minus 1 is 0, I get this equation here, which is known as the Ratchford-Rice equation. And the Ratchford-Rice equation, again, it's just taking these equations and combining them together and doing some algebraic manipulation. It's the equation here that tells us a valid solution of a multi-component flash drum. And once we've gone and found the right parameters that make this left side equal to 0, then we have a correct solution to the Ratchford-Rice equation. And notice again that it's a nonlinear equation, so all those nonlinear techniques that we've been playing with previous class, that's what we're going to come to play. So when we're solving this type of equation, we oftentimes will either have to do a guess and check method, or we may have to use Excel, goal seek or whatnot. But solving this just by pure algebraic manipulation is very difficult, so it's a nonlinear equation that we have to worry about. So let's just go through a typical problem again, where we have this flash drum. We know the properties of the feed, its mole fractions of the feed. We know the total pressure, or we know the total pressure in the flash drum. We know the temperature, and we're asked to find again the outlet compositions and the outlet flow rates. Here's the equation that applies. So how are we going to do this? Use this equation to go about solving for these unknown properties or unknown variables. Well, first thing you notice here, we need to know what K's, we need to know the Z's, and we need to know V over F. Well, we know the Z's, that's given right here, so we know all the mole fractions of the feed. What about K's? Well, we need a way to find the K values, and we can find them from the known information that's given to us. So for instance, we're told the temperature and the pressure. We're told the temperature and the pressure, and from the temperature and pressure, we can calculate the K values. How do we do that? We can use, for instance, our Raoult's law equations. Our Raoult's laws allows us to calculate the K values based off the temperature and pressure. So again, step one, get the K values, and here I've written out the K value equation based off Raoult's law, and it just says that K value is equal to the vapor pressure of the pure species I divided by the total pressure. We know total pressure. Vapor pressure, well, we can calculate it because we know the temperature, and we can use Antoine's equation, so we can calculate the K values for each individual species. So we know the K values. At this point, we know the Z values. What are we going to do next? Next, what we're going to do is we are going to go ahead, take this equation, and we're going to find the V over F value that satisfies it. So we're solving for the variable V over F in this very nonlinear equation. And we can do this again using plug, chug, Excel, whatnot. So we go through some iterations and we find the V over F that satisfies this equation. Next, what are we going to do once we've found V over F? And the last step here, step 3, is to find the xi and the yi values, and this is where the two equations we use. We know all of the parameters in these equations. We just found V over F in step 2, so we know this value right here. We know the ki's, which we found in step 1. Zi's were given to us in the problem statement, so we can find out what or find out what xi and yi are for each individual component. And at that point, we pretty much know everything. With V over F, we can calculate the vapor flow rate, and we can also calculate the liquid flow rate. We know all the mole fractions in the liquid and the vapor, the xi's and the yi's, and that's the way that we go about solving this type of system using the Ratchford-Rice approach of a multi-component flash drum system.